toolware, and cut geometry on the product. And then the real world application is the 18 parts that we're going through and capturing real-time data, and how we're going to be able to use that data to manage not only product quality, but also energy efficiency in the process. And then he'll wrap it up with some discussion about off-the-shelf solutions that some of you in your manufacturing processes can take back, and certainly can work with MEP or CCAT to kind of figure out how you can take these low-cost opportunities and turn it into some real production improvements. Just a quick background on us. We're a big utility company in 3 states, as I try to accelerate here. We have 4 million customers in the 3 states. We serve electric, natural gas, and water, with over 9,200 employees serving those customers. And we spend about $700+ million a year on energy efficiency to help our customers. CCAT, the Connecticut Center for Advanced Technology, is a technology and education demonstration center that assists our customers in Connecticut, and actually outside of Connecticut as well, to improve and adapt new technologies, leading edge technologies for their operations. They provide education services, and they help small, medium, and large manufacturers really engage some leading edge technologies. You can talk to Nasir, and there's some other folks here from CCAT as well that you can talk to. So how does Industry 4.0 energy come together? What we're really looking at is taking machine learning, artificial intelligence, which has got a bad rap since ChatGPT has come along, but essentially we're going to be looking at using machine learning, artificial intelligence to help inform us on how do we make a product and optimize the efficiency of manufacturing that product. If you've worked with us as a utility company, you know we provide incentives to our manufacturers for energy efficient lighting, HVAC systems, air compressor systems. We're looking to always help our customers find energy efficiency in their process, in their operation. I can tell you that we haven't really had a deep dive into manufacturing processes, and that's really where there's additional energy savings that we know we can find as we start to look at using these technologies to get inside your manufacturing processes. So, in fact, our relationships are probably with plant managers, maintenance people, facilities managers, but we probably don't have a lot of relationships with the guys who are involved in the production side. And that's really what we're hoping to learn in this process. And through this demonstration project, we're hoping that we're going to be able to find ways to help you either with incentives or some technical support to help you move into the Industry 4.0 world. Well, here's a demonstration project. We engaged CCAT. We identified basically through a CNC process, we're looking at 18 steel billets that are going to get milled or have been milled through a CNC process. And we've captured a ton load of data in that process, including power, including from inspection processes. We've looked at cut geometry as well as toolware. That information is going to be taken into phase 2, where we're going to now implement some numerical control software that's going to help, based on the phase 1 data, to try to optimize what that looks like, and then take that into phase 3, which is the adaptive control. So we're doing this real time. We're taking real-time data, adapting the process, the manufacturing process, though, so that we're actually making better parts, reducing defects, getting better throughput, and reducing the energy consumption at the same time. So Nasir is going to take you through the case study and the deep dive into the actual data that we're getting out of the process. Nasir?
Thanks, Bob. Good morning, everyone. I know that lunch is supposed to be at like 12:10, so I've got 20 minutes to do a 40-minute presentation. So I'll skip through some of the slides. But yeah, so as Paul mentioned, my presentation is set up in 3 parts, right? The first part is going through a very simple case study to help you understand what the benefit is of adding sensors to a machine, collecting that data, what you can do with that data, and how it affects costs. At the end of the day, how it affects costs in manufacturing. Then the second part is showing you a real world example, having now understood from that simple case study the benefits, how we apply that to real world. And then the last part is the takeaways, right? What are you going to take away from this presentation? What are your kind of call to action? So I'm going to present some of the off-the-shelf solutions that you can start to investigate, having now the knowledge of what this kind of technology does and how it can be beneficial to your company. There's several different ways in which you can apply what I'm going to be showing you next. So we'll start off with the very simple case study. The machine you see on the left there is one of my favorite machines at CCAT because it is a legacy machine. And the reason I say I love it is because it relates to a lot of the mom and pop shops that are out there. A lot of companies have machines that are not necessarily the newest or have any standard communication protocol built into them, such as MT Connect or OpenCUA or MQTT or some of the other ones that are out there. It is a bare bones machine. I basically have a serial connection to the machine and that's it. So starting off with that as the basis for the first experiment, what we want to do is add sensors to the machine so we can collect some manufacturing information off of it. So what we did was we bought a current voltage transducer and an Arduino board with an analog digital converter. $200. $100 for the sensor, about $100 for the microcontrol board. And we added it to the main power supply that goes into feeding each of the 4 motors on the machine. That's the X, Y, Z axis and the spin motor. So, well, essentially what we're getting is overall system power consumed, right, as we're producing the part. And this was the experiment. We start off with a 7-inch diameter stock material. It is an alloy steel, about medium hardness, and the stock is about 1/2 inch high. The machining tool path you see is second to the left. Very simple. We start out from the outside and do a spiral path inwards to end up producing a 3-inch diameter cylinder, and we go down 4 times, each at 100 thousandths axial depth. So we end up with a 400 thousandths by 3-inch cylinder. We use a tool that uses indexable inserts just so that we can do some tool wear measurements under the microscope, and then the resulting part on the right there. Very simple part. We're just after a 3-inch diameter cylinder. These are the results of cutting 8 parts. So what you're looking at, the graph at the top left, is the measurement of the cut diameter of the tool. So the way we did this, initially we were going to take the indexable inserts off and measure the flank wear on a microscope. But that's not practical in the real world if you want to apply this kind of technology. Instead, what we did was we had fixtured next to our stock material some soft aluminum, 6061 aluminum, and we did a really slow plunge cut into that aluminum at 100 thousandths axial depth. The reason we did 100 thousandths was because that's the amount that we were going down at for each cutting point. And we ended up measuring the diameter of that plunge cut. That gives us the cut diameter of the tool. Very, very simple method. Anybody can do it. You don't need an extra sensor. You just need an additional path in the NC program to be able to do that. But what we're looking at the graph at the top left is that we maintain a pretty consistent cut diameter from part 2 to part 6, and then it plummets after that. And the reason you're not seeing part 1 is because we use part 1 to validate the path is working correctly. That results in, if you think about this, right, because my pathing is starting out from the outside in, as my tool cut diameter decreases, that's going to result in my cylinder diameter increasing. And you see exactly that, the graph at the bottom left. You see that from producing part number 2, we're at about 3 inches, 1,000. And by the time we get to part 8, we're 25 thousandths off. So it increases quite drastically right around part 6 when the tool just wears down to a significant amount. The graph at the top right is the signals we're getting off the machine. So I'm just showing you two signals for producing two parts. One is part 2, which is the green signal. And then the blue signal is the amount of power consumed by the spindle cutting part A. So what you're seeing here is at the beginning where I'm engaging in the material, you see a little bit of a spike in the power consumed by the system. And then as I'm actually getting into cutting my spiral, and I'm digging into the material at at the extreme, my signal is hovering around a certain amount of power consumption. Right away, you can see that from part 2 to part A, I've increased my power consumption by 500 watts. And if we take a look at this data and correlate it with my, the actual resulting dimension of my cylinder, we can come up with this model. And in this case, this is a very simple model because we're only using two points. One is that we know that we're consuming 2 kilowatts of power to produce a cylinder that's 25 thousandths off. And the second point is that we know that we're consuming 1.5 kilowatts of power, producing a cylinder that's 1 thousandths off. If we just do a simple line fit, a line equation, we can estimate that if I'm seeing 1.75 kilowatts of power consumed by my motor, I can predict that I'm going to be 12 thousandths off in my cylinder dimension. So in this very simple case, you can see the power, the benefit that we're getting off of adding $200 of sensors and a control board onto the machine. Getting that data and doing the correlation between the signal, the real-time signal we're getting to the dimension of my feature, we can right away see that we're now going from measuring the part after production, where we can say, whether or not that part conforms or doesn't conform. If the part is out of spec, if there's nothing that we can do to correct, the part, it's essentially scrap. So all of the energy that went into producing that part is wasted. And you can back calculate that to carbon footprint, to parts produced per day, overall efficiency in your manufacturing plant. But at the end of the day, you're putting a lot of energy into producing a scrap part, right? So if we can even just avoid that, that would give you a huge benefit in manufacturing. So the model itself is good. It's the application, right, of that model to a corrective action code that actually gives you the benefit. So here we're predicting the value of our feature in real time. So we can predict when something is going to go wrong, and then that prediction can go into a corrective action algorithm that in this case can change the tool radius offset of the tool in real time to account for the radius decreasing. Now this is on a machine that has no other sensors built into it, there's no way of communication. So on a very bare bones machine, by adding $200 of sensor and a control board, we're doing corrective action. We're doing adaptive control on the machine. So this graph, very simply, on the x-axis we're looking at tool wear. On the y-axis we're looking at expected dollar costs. And you can see right away that with a default control, that is not using the supervisory control versus using the supervisory control. As the tool wear increases, you increase in the potential cost savings. So there's a huge benefit here by leveraging the data you get off. So in real life, though, there's a lot of different ways in which you can produce parts. It's we're just showing a simple milling operation, but you can have hole drilling, facing. There's other manufacturing types, not just CNC manufacturing. And there's a lot of different sources of production variability. So if we list out some of them here specifically, now we're getting into our second second case study, which is producing actual parts on a machine that does have connectivity, that is a more recent machine. In our case, it was a DMG LaserTech 65. It happens to be a hybrid machine. We were just doing 5-axis machining on it, and it uses a numeric 840 DSL control. So if we look at some of the sources of production variability, we can start with stock deviations. So in the simple example that I gave previously, if I didn't start off with a 7-inch diameter cylinder, let's say it was 7.5 inches, or let's say it was 7 inches and over 1,000th inch, right? My first pass is going to show a lot higher energy, energy usage, as compared to maybe stock material that was 7 inches in diameter. If I hadn't known that my stock material was bigger, I wouldn't know what's contributing, or I wouldn't have a one-to-one correlation between why I'm seeing an energy spike, right? And I could associate that with tool wear. But in this case, if we took the measurement on the stock material before it went in, we have another data point to use as a way to figure out what's causing that variability. So if you can get simple measurements, size, hardness, grain orientation, porosity, inclusion, if you're using castings, forgings, that can play a big role. Temperature, you can get a quick temperature measurement on the stock material before it goes into the machine, or if you have a way to measure bolt stress. If you're squaring up the stock material, and if you do that with an EDM process and you take a slight sliver cut, you can see if the material actually bends away or towards the cut. Your machine variations. So my spindle speed, and my axes, overrides. There are programmed paths that the controller has to hit, right? There are planned programmed positions where that tool has to go. Is the controller actually capable of getting that tool to that position? Is the speed at which I program the NC path to machine at actually being accomplished, right? And then you have other things such as coolant. What is the temperature or viscosity condition of my coolant? And then tooling, of course, is one of the biggest contributing factors. And then technician distinctions. If you're starting to hear chatter, if you're starting to hear some noises where the technician has the ability to override speeds and feeds, that can vary between technician and technician because of experience, training, and preferences. So these are some of the sources of production variability. What we're looking at here is an overall architecture of trying to capture a digital signal across all the different processes in producing a part. So it starts off, I'm showing model-based definition. Is everyone familiar with what model-based definition is? Model-based definition is essentially a digital source. It's a machine consumable data that you can use right away. It encodes the nominal dimensions that the features have to be produced to. It also, if it has an embedded PMI, you know the tolerance within which each feature has to be produced, and any other specifications such as surface roughness, any post-production operations that have to go on it. But the important thing here is it's in a digital format, so you start off with a digital format. Then your stock material, again, if you can get a quick hardness measurement, length, width, height, if you're starting off with a casting forging, if you can use a scanning device to quickly digitize the actual stock material. Any form of measurement you can get on the stock that captures a digital signature of the stock material before it goes into machining is beneficial. Then you have your production system, so you can add an edge device, Ethernet connection to your machine. It allows you to subscribe to the control parameters on the machine. That's all a digital signal. It also can get any overrides that the operator does back on the edge device. And then your post inspection. So if you're using a CMM or a laser scanner, structured light, any kind of, even a calipers that have digital readout to a central system, any kind of inspection system that gives you back digital information. So again, digital, you want to digitize your entire process, because what we're doing now is everything from the production leftwards is going to go into feeding our parameters. It's the definition or the information that constitutes your manufacturing process. And then you have your learner, which is with all that information we collected during our manufacturing process, what is it resulting in? What is my part quality? What is my feature accuracy? That's the learner component. So these two feed into the machine learning algorithm that generates a model. And that model can then be used for predicting what the quality of my part is going to be before the issue arises. The benefit there is only realized in corrective action, right? If you're not applying corrective action, you're gonna know you're gonna produce something bad. You're gonna produce it and then measure it, and basically be certain that you just had an accurate prediction, right? That's the way in which you can calculate the accuracy of your prediction by not applying the corrective action and seeing the actual result compared to your prediction. That's going to be important when I talk about accuracy and about the different codes that are out there. But this, in essence, is essentially saying that in this case, AI and the subset machine learning is incredibly important because in our previous example, we only looked at the power consumed by the motor to produce a 3-inch cylinder. And my machining path was such that I exerted a lot of force, or the tool saw a lot of cutting forces, which resulted in higher power consumption. And it's on a Haas mini mill that uses a small spindle motor. So the amount of power increase was significant enough for us to actually visually see the correlation between the two. But what if I'm drilling a small hole? What if I'm using a very small drill and I'm using a machine that has a spindle motor that's so high in horsepower that the significant change, right, in the power consumed because of tool wear is so little that it's insignificant compared to the feature dimension change. So in that case, there are other parameters, right? There's actual axis position, there's torque, there's load. There's so many other signals that we can tap into to see how they correlate to the feature dimension. But given that we're getting more than just one signal, how do we assign the appropriate weights to each of the signals that contribute, right? So for example, in a hole drilling operation, perhaps the torque signal is 50% weight because I can see that the change that I'm seeing in the signal as the tool wears is more significant than the power change, right? So the power signal I may want to give a 5% weight, and then so on and so forth for other signals that I'm capturing. Well, machine learning does this completely automatically. It has the ability to identify those signals that have the highest contributing factors to the end measurement. Even if I was to apply statistical models, I would have to still manually assign those weights. Using machine learning is a complete black box operation. You feed it information, outputs a model, and that model automatically assigns the weights. So it's kind of a no-brainer. Going with machine learning in this case is incredibly important. Where AI comes in is where the corrective action actually resolves the issue. That's the autonomy part of it, right? Where the system itself has the ability to sense something's going wrong, and it has the ability to automatically adjust for the things that are going wrong. That would complete the AI, the overall code. So here I'm just going to go into a little bit of the details of the connectivity of the edge device to the machine. So it's very, very straightforward. The edge device itself has 2 Ethernet ports on it. One Ethernet port is for connection to the machine controller. In this case, because we're using a cinematic control, I'm pretty sure that almost all Siemens controls designate a particular port called X120 port that is assigned for connectivity. The other port on the edge device is a connection to your network. Now there's 2 reasons for this. One is so that you have an interface into the edge device. So on your network, you would bring up a browser, a web browser. You would type in the IP address of the edge device, and it would bring up the interface to the edge device, whereby You're able to install software, you're able to adjust parameters on that software. The other component is connection to MindSphere. So MindSphere is Siemens' IoT cloud platform. It's kind of like Google Play Store or the Apple Store, where it holds a lot of different applications. You can browse and read about what those applications are. You can pull those applications into the X device and install them on the X device. So the setup here, this is the part that we produced. It was designed specifically to have as many features as we can fit on a 4x4x4 inch part. A lot of the common features that you would find in manufacturing: holes, counter bores, facing operations, pockets, slots. Even on the other side that you can't see in this picture is a 5-axis swarf cut. So we incorporated a 5-axis path in there as well. But you can notice that we're using model-based definition because the model encodes the nominal dimension, and then for each of the features, we have assigned a feature control frame that holds the tolerance within which that feature has to be created. And then for each feature control frame, we have a feature ID number assigned to that particular feature. On the top right, we have the manufacturing operations. And then at the bottom here, we have a mapping file. The reason we need this mapping file is because one manufacturing operation may result in many different feature IDs being created. As an example, in a pocket, it's one machining operation with a flat end mill, say for example, that creates a width, a length, and a height, right, of a pocket. So we need to know what manufacturing operation relates to feature ID. And that goes back into feeding the inspection data. So if we know the result of the feature dimension, we can then back correlate that with what manufacturing operation created that issue or created that feature. So these are the signals. Again, we chose to subscribe to 92 different parameters that control parameters from the machine, and we're getting each of these parameters at a frequency of 500 hertz. So you can imagine even a 5-minute cutting operation produces a ton of data. In fact, it's so much data that if you were to go through it manually, it would take you much longer to come up with that correlation between the different signals and the resulting dimension of the feature. What I'm showing you here on these 4 graphs are just one of the signals. This is the power consumed by the spindle. The reason I'm showing the power consumed rather than some of the other ones is because it relates back to the first case study, the simple case study. And I'm only showing the signals for producing 4 of the features on the part. So on the top left, we're looking at feature number 10. That's a side. It's a pocket on the top of the part, and you're seeing just the signal for that manufacturing operation to cut that pocket across with the 18 signals from the 18 parts laid on top of each other. And you can see right away there's a variability. In fact, on this particular feature, there's 18% variability across the 18 parts. The graph at the top right is showing you a hole drilling operation, and this is a hole that goes right through the 4 inches. And so you can actually see one of the signals is spiking quite high because we had some chip compacting going on there, and it threw off my percentage to 158% variability. But if we ignore that, this data here is about 20% variability. At the graph at the bottom left is producing feature number 8, which was that 5-axis feature that we incorporated into the part. And you can see across the 18 parts, 17.6% variation. And then the graph at the bottom right is showing cutting feature number 2, which is a slot. And again, 25% variability, right? Each of these are just 4 of the features. If we look at all of them, on average, we were looking at about 20% variability, right? It's not 1 or 2%, it's 18% variability, or 20% variability. So it's significant enough for us to see the benefit. And the reason I'm showing only the power consumed by the spindle is that if we were to apply corrective action, we could get 20% energy savings by mitigating the problem. So I'm not even, we're not looking at all the other 5 axes, right? The X, Y, Z, the A and C axis motors. We're only looking at spindle power. So if you even take this and extrapolate it out, you can save a significant amount of energy by applying this, by having an AI system control your manufacturing variability. So what we ended up doing was, after the part was produced, we wanted to measure it, obviously to get an understanding of where the dimensions were for each of the features. And we did it across 3 different machines. The reason we did this was so that we can see how the accuracy of the measurement equipment affected our prediction accuracy. So we used a GAM ATOS, we used an M3DI, both of these are structural light scanners, and we used a Renishaw equator, which actually has to use a CMM for the master part, and then you measure all your subsequent parts based off of that master measurement from this. And the results I'm going to show you in the next slide are off of this feature number 37, which is the flatness call out on that face that's highlighted on the part on the left. On the left, you see the measurement of the flatness. So it ranges from 1/1000th of an inch up to 1.75 thousandths. And then the real-time data that we're getting off the machine, this is just the power signal. Again, one of the 92 different parameters that we're getting. But even that, you can see it has 9% variability in the signal. So right away, you can see there's a correlation, right? If my variability here was 0.1%, but my variability there is more significant than 0.1%, then I know that the power signal is not the major contributing factor to my variability. Something else is causing that. So let me take a look at torque, or maybe it's the actual axis position, because in a facing operation, in this case, I have X and Y and Z. Z is essentially goes to a certain position and stays there, and then X and Y axes move, right? But then I also have tool wear, and I also have, there's other contributing factors like, my stock material dimensions. Was it flat to begin with? Was it varied? As I'm cutting the part, imagine the tool itself is wearing as you're cutting. So how does the undulations in the surface of my stock material have an effect on my tool wear? So suffice to say, this is again just to make the point that machine learning takes care of this automatically. We don't have to worry about it. We just feed it the data, and it figures all that out for us. So the next graph, what I'm going to show you here, are the results of pushing this data through different machine learning algorithms. So there's standard ones that are off the shelf, and then another one that we're in partnership with the University in Connecticut to produce a custom algorithm, because our testing was done on producing 18 parts. One of the things and the benefits about machine learning is it can give you very high accuracy predictions on data that it has seen before. Okay, if it doesn't have the information, it can't give you an accurate prediction. And so, that being the case, you want to feed as much data into a machine learning algorithm as you can. So you want between 50 to like 100 different data sets at the minimum, right? And in our case, we only used 18 parts. So what we're seeing is across, if we use only 18 parts, standard machine learning algorithms only produce at most 63% accuracy. There's a lot of machine shops that I work with that have high mix, low volume. So for those machine shops, we didn't want to have a circumstance where this is not beneficial, which gave rise to the development of a custom algorithm that can give you high accuracy even on low volume data. Right? That's the thing. The other flip side, and what we're contributing to this algorithm with the University of Connecticut, is the way in which we look at how we're training. So on our particular part, we have many holes, right? If we train the data based on feature type, we can be training on 16 holes that we're producing on our particular feature times 18 parts. All of a sudden my data set is increased quite significantly. So we can do training by feature type, we can do training by material type, by the tool used, by machine, or by the entire operation across many different tools. So our prediction is as good as the data we feed it. Some of the obvious, outcomes of this is presented there. You get status monitoring, adaptive control is the big one. But again, the point I want to make here is with the information that we're getting, what we do on the corrective action side is not only control the tool radius offset of the tool, but adjust the feed and speed overrides in real time on the control to bring that energy consumption down, so that you get the result is getting consistent measurements across your parts while reducing your energy consumption, reducing your scrap rate, which increases your parts produced per day. So we can, overall, you can kind of summarize the benefits there. The next portion, and I know I'm kind of cutting into the lunchtime here, is the third portion, which is the takeaway. If you get anything out of this presentation, is when you go back to your manufacturing businesses, what are some of the tools that you should be looking into and investigating? This is just a small list, but if you want to reach out to us to get more information, we'd be happy to point you in the right direction based off your particular needs. I have to present the Siemens solution because that's what we exercise. That's what we use in our case study. So again, simple X device, very simple connection to the machine. Download a piece of software and you're off and running. It's a very simple integration. Something that's a little bit more involved is Siemens adaptive control and monitoring. They call it the ACM. It's an additional piece of hardware that gets attached and works in tandem with your controller. In this case, it can be any machine controller or any kind of machine. And essentially it does the adaptive control, it does the learning operation. You don't have to be connected to the cloud. It is a little bit more of an installation on your machine, and it is a little bit more expensive, but it's a plug-and-play solution. 10 to 30% shorter machining time, because one of the things that it does is that if it sees the loading on the tool is minimal, it'll actually increase the feed rate. So if you're doing a lot of air cutting, if you're machining castings, or that may be they have quite a significant amount of variability sometimes, and you have a set program and you're just cutting air, it'll speed up the feed rate there, so you can actually show them the value of cut time. You have care and engineering tool monitoring and adaptive control. Again, cycle time savings of about 20 to 60% because it looks at kind of evening out your loading on the tool by increasing or decreasing your feed rate. If you don't want to have a hardware solution, there are some software solutions as well. Maybe there are machines that are you don't, for any particular reason, don't want to add additional hardware on, or you can't add hardware on, or you can't have connectivity to it because of cybersecurity problems, right? In this case, you have software solutions like from Third Wave. They do everything I just discussed on a physics-based model in a simulation environment. So if you give it your tooling information, you give it your shop material information, you give it your NC code, and it actually virtually cuts out your part and calculates all the forces that are seen by the tool, and then it optimizes your machining program so that you can then take that program, put it on the machine, and start realizing the benefits of it right away. And the last one that I'll present here is Vericut. You may be familiar with Vericut. It does very similar calculations to what Third Wave does, except on a little bit more simpler scale, and it looks at chip load, and it optimizes feeds and speeds based on the chip load. So the output of this is an optimized NC code that you load onto your machine and execute. So again, any further questions, please reach out to MassMEP. Feel free to reach out to myself or Paul, and we'd be happy to answer any additional questions. Please do investigate some of this technology if you haven't seen it before. It can, I hope the takeaway is the benefit that these technologies have to controlling manufacturing variability, so you're increasing your throughput and you're getting higher quality products out the door. Thank you so much.